Swayam Prabha. Digital India. Educated India.
Hello and welcome back to another lecture on this course called Robust Control. So, in the last lecture or so, we started doing a sort of a refresher on topics from linear algebra. So, for those of you who are already interested or aware of these topics, it might seem a bit of repetition, but I'll chance that repetition, and at the cost of being repetitive, I will still go through a quick recapitulation for those of you who are already aware, and maybe an introduction for those of you who are not familiar with these topics on linear algebra, followed by some ideas from matrix theory, and then maybe some familiarity I'll try to develop on things like linear matrix inequalities, which we shall be using then gainfully throughout our course. It will be a very important part of this course. And once we are done with this refresher, I know I had promised this maybe a couple of lectures back, maybe in the introductory lecture, to give you an example. So, remember where we are currently standing with the motivation of our problem. We have a system in which we managed to pull out the complicated part of the dynamics, whether it's a higher order part or whether it's the nonlinear static part. We managed to pull it out of the linear part of the dynamics, and then we say that the advantage of being able to pull out this complicated part is that you can then approximate or replace this complicated dynamics using a set of simplified dynamics, right, and then assess the behavior or performance of the system over this class or this set of simplified dynamics, right. So, over a class of uncertainties, which we represent by this set called big delta, right. So, after we have wound up with this refresher on linear algebra, matrix theory, linear matrix inequalities, which could be maybe in 1 or 2 lectures from now, we will finally give you an example of one particular case where a particular sort of a model of Q, that is the complicated dynamics, which can be captured by a set of simplified dynamics, maybe a linear map, set of linear maps, okay. And with that we would be in a perfect place to launch into the heart of this subject. So, again then we will go into this some basics of control theory, which will also require some understanding of these topics that we are covering now, that is on linear algebra, but more on that later. So, I haven't forgotten that promise that I made a couple of lectures back maybe of giving an example of how you can replace a complicated dynamics by a set of simplified dynamics. So, rest assured we will give you one example. So, now in the last lecture we ended on this description of what is a vector space. Again, this is a semi-formal treatment, so I have not really started with the description of what a field is. I am just assuming that you understand the most important properties of complex numbers and real numbers, and for our course here it would suffice if you just understand those properties, right, and then I would just put it to you that, well, these complex numbers, the set of complex numbers and the set of real numbers, these are what qualify as fields. These are not the only examples of fields, but these are 2 typical examples of fields that we shall be concerned with for this particular course, and therefore I have not launched into a definition of what a field is, right, because that might take us too far afield and into very rigorous treatment of linear algebra, right. We are trying to keep it a little semi-rigorous here. Okay. So, in the previous lecture we have described to you what a vector space is, and then we have also described to you what a subspace is. So, we saw that if you have a set V, a field which in our case would be complex numbers or real numbers, and two operations, the vector addition and the scalar multiplication, which satisfy certain properties, 10 of them to be precise, as I listed in the previous lecture, then we say that this is a vector space over the field F, again, which in our case is C or R, complex numbers or real numbers, right? And then what is a subspace? Well, if you take a subset of that set V and you inherit the same operations of the original vector space, and then that subset of V satisfies all the properties of a vector space as well, yeah, then it becomes a subspace of V, not just a subset of V then, right? If that algebraic structure still holds over the subset of V, then it's also a subspace, right? So, to give you a quick kind of an example of what a vector space and its corresponding subspace could be like, we'll of course delve much more into much more details of matrices. But for example, let V be a collection of all n cross n matrices over. So, V is defined in such a manner that V is this, okay. So, by V I mean this is a vector space now. So, V, yeah, we are defining as this over R, right. Yeah, we could have taken complex numbers as well, complex matrices as well, just let us take the real matrix for instance, right. And now you define the set S, which looks like a dollar symbol to be honest, yeah, as well, the set of all matrices n cross n over R such that A belongs to S n cross n. Actually, I could have just made matters simple here. Let me just use the set theoretic notation here, right. That would make matters much simpler here, sorry. So, let us say this is n cross n, yeah. So, this is basically all matrices A that belong to R n cross n, or I could have replaced this by V as well, such that A transpose is equal to A, right. Now, I leave this as an exercise for you to check that this set S n cross n that I have defined is a vector space. By that I mean that you have to essentially check whether it satisfies all of these properties. Of course, by addition, vector addition, I mean the conventional addition of matrices applies here, right. That is the operation that I am defining. And scalar multiplication means when you multiply a matrix by a scalar, then every entry of the matrix gets multiplied by the same scalar. In this case, the scalar is from the field of real numbers. Yeah, so just subject to those two operations, you can check very easily that all of these 10 properties hold. In fact, there is a very easy way of checking. Yeah, it's just the the superposition principle basically. So you take any two members from the set. Yeah, so if you want to check for a subspace, here's the quick check, because already the original parent space satisfies all the properties of a vector space because it's a vector space itself. Now the subspace also has to be, the potential subspace also has to be a vector space, right. Yeah, something that you're checking for its potential applicability or potential definition for whether it can be defined as a subspace, yeah, given a set. What you do is you pick any two members from that set. So, to check if W, or let me use some other symbol here, maybe not W, let us say V1. V1, which is a subset of V, is a subspace of V, do the following. What do you have to do? Pick up V1 and V2 belonging to this subset V1 and check if alpha V1 plus beta V2 belongs to V1 for all alpha beta belonging to the field, which in our case is of course either real or complex, as the case may be, as we have chosen, right. Yeah. So, you do this for any two elements V1 and V2, and you do this for every element likewise. Yeah. So, first you pick out any two, if it holds true for all of them, then you pick out any other two if it holds true for all of them, yeah, for all values of alpha and beta, and you will see that just by checking for this is an equivalent check. Just checking for this property is equivalent to checking for all of those 10 properties. Yeah. So, you can suitably choose your alpha and beta in such a fashion, in a clever way, to show that each of these properties will be satisfied if and only if this test is passed, right. So, that is a effective way of checking whether a particular subset of a vector space is also a subspace thereof, right. Anyway, we will not get into this, you can just try this as an exercise if you are interested, and these are things that are generally discussed in standard textbooks on linear algebra as well, right, but these are properties that we use most often, these prove to be very handy, yeah, so it is good to know, right. So, maybe the idea of, I hope the idea of a vector space and a subspace have at least been clarified. I know I am going through this a little quickly than maybe a course on linear algebra would warrant, but then I might remind you that this is not really a course on linear algebra, so we would have to do a sort of a quick recap in any case. Nonetheless, if you are really interested, as I say, please visit these topics from some of the excellent textbooks that are there, yeah, available on the topic of linear algebra, right. I invite you to do that. Okay. So, now having described what a vector space is, what a subspace is, we are now going to take some more typical examples of a subspace. Okay. All right. So, suppose we are given a collection of vectors, say set V1, V2 dot 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 till V, what is the number, Vn, yeah, it is all right. Okay. Then we define this, and I leave it again as an exercise for you to check that this is indeed a vector space. We define the span of these vectors that belong to this set Vn as equal to, and this is the set theoretic notation that we are going to use now, the collection of all such vectors V such that there exist alpha 1, alpha 2 dot 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 till alpha n in the field of scalars. Again, this could be in our case R or C, I cannot overemphasize this because we are not going to look for other sorts of fields, even though there are several such fields that can exist. For our purpose, it will either be R or C. Okay. So, if there exists these satisfying V is equal to summation alpha I Vi for I going from 1 through n. In other words, if you have a vector which can be represented in the following manner such that V is given by alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3 so on and so forth till alpha n times Vn. So, remember this is a scalar multiplication that is there in the defined in the vector space, right. And then when we sum this sum is basically the vector addition that we have defined in the vector space. So, just to be sure that we are not doing any illegitimate operations or some undefined operations, both of these operations are defined. When we are multiplying alpha 1 times V1 or alpha 2 times V2, those are in the sense of the scalar multiplication that the vector space already contains within itself, defined. And when we are adding them, alpha 1 V1 is a vector that belongs to the vector space quite simply because of the closure under scalar multiplication. Alpha 2 V2 likewise also belongs to the vector space by dint of the closure under scalar multiplication. And then alpha 1 V1 plus alpha 2 V2 also belongs to the vector space by dint of the addition of two elements from V also belonging to the vector space V itself, that is closure under vector addition. And now you go by whether you like to call it mathematical induction or whatever, yeah, you can just extend it. You add first two elements, and because it is associative, it does not matter in which order you add. So, all those properties that we have defined for the vector space, you see, they give us the luxury of defining a set like this without any care in the world that we are doing something illegitimate or something that we have not defined, or we are violating something. No, we are not, because all these operations, this summation, the scalar multiplication, and saying that something is equal to something on the other side, left hand side and right hand side of the equal to sign, yeah, these are all legitimate operations, specifically because the structure on which we are the structure on which we are building all of this is very well defined. It is a vector space, right? That is very important to understand. Now, so therefore, what we say is that this is how we define the span. So, you give me a set of vectors, a collection of vectors, countable collection of vectors, and I give you this set. I can always define a set like this, and once I have this set, it is this set that I call as the span of those vectors. Now, again I leave it to you as an exercise to check that the span of a set of vectors is also a vector space. In fact, you see that if V1, V2 dot 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 till Vn, yeah, all of these actually belong to the original vector space, then the span of V1, V2 likewise till Vn is actually not just a subset, but rather also a subspace of the original vector space, right. So, if it is a subspace, it has to be a vector space in its own right. So, then this is kind of like a no brainer, right, that the fact that it is also a vector space. So, you check, yeah, take these as small bits and pieces of exercises, and in doing in sort of performing these exercises, these ideas will be crystallized. Yeah, if you are already familiar, even then it does not hurt to try this once again. If you are not familiar, then you should all the more have all the more reason to try these, because these will familiarize you with how we go about proving things in an abstract domain, right, because this idea how to go about proving things in an abstract domain is going to be very handy throughout this course, right. We are going to be doing a lot of these abstract proofs in this course. So, the least we can do is to at least try some of these introductory proofs from linear algebra, right. Okay. So, all that you need to basically do is you take any two vectors, let us say what should I say, P and Q, okay. So, let me just give you an outline of the proof. Yeah, let me not leave so much, because this is the early days of this course. So, yeah, so outline is P, let P and Q belong to span of V1, V2 likewise till Vn. And now, as I said, just notice how do you check whether something is belonging to something is a subspace. So, you pick any two arbitrary. So, P and Q are not something special, right. So, you might say I have said pick up this. So, if you pick them arbitrarily here without assigning them any special property, then if this holds for any two arbitrary members of V1, that you take them, multiply them through two scalars, to any two scalars, and then you add them, yeah, and if they also belong to this putative subspace, which is now up until now just a subset, yeah, then what you have on your hands is essentially a subspace, right. So, we will do that same, we will use the same idea to check if it is indeed a subspace. So, let us take any two arbitrary fellows P and Q from this span. So far we do not know whether this span is a subset or also a subspace. Of course, it is a subset, but whether it is a subspace or not, that is exactly what we are trying to prove. So, you pick out any two of these. So, if P belongs to this span, then definitely P can be written as, I mean I am just omitting some of those steps. So, P can be written as maybe some beta 1 V1 plus, because after all that is a definition of something that belongs to the span, right, and this is beta n Vn. And then Q can also be written as gamma 1 V1 plus gamma 2 V2 plus gamma n Vn, isn't it? Right? We can do that. There's absolutely nothing stopping us from doing that. Now, if you want to check whether alpha p plus beta q, what does that look like? Well, it will look like beta 1 V1 plus beta 2 V2 plus beta n Vn plus beta times gamma 1 V1 plus gamma 2 V2 plus gamma n Vn. And if you, because you know that this there's this property of associativity of the scalar multiplication. So whether you multiply alpha with beta 1 V1 or you multiply alpha with beta 1 first in the scalar field and then you multiply the resultant scalar with V1, it matters not, right. So look how these important properties that we defined the other day as attributes of a vector space, they actually serve a purpose. When we talk about conventional operations that each of us is familiar with, we don't even give these things much thought because we know we are dealing with numbers. But each of these ideas particularly gets more important as we deal with structures that are not necessarily real numbers and complex numbers. So maybe for this course you will not really be completely able to make out the difference that these properties make. But be assured that these are very important properties that this vector space brings with itself by virtue of the way it's defined. So, all right. So then what we can write is alpha beta 1 V1 plus alpha beta 2 V2 plus till alpha beta n Vn plus beta gamma 1 V1 plus beta gamma 2 V2 plus plus beta gamma n Vn. Now we collect together the coefficients of V1, V2 likewise, and you can immediately see what picture we have. We have alpha beta 1 plus beta gamma 1 times V1 plus alpha beta 2 plus beta gamma 2 times V2 plus so on and so forth till alpha beta n plus beta gamma n times Vn. Now let alpha beta I plus beta gamma I is equal to, for want of a better term, let me call this delta I, or let me not use delta because in this course delta has some other significance later on. Let us call this just just nothing fancy, just Ci, all right. So then what we can continue to write is this is nothing but summation Ci Vi. But what does that mean? If, remember, this vector that we are trying to check for, this vector can actually be written in this form. In other words, alpha p plus beta q is equal to summation Ci Vi. This merely implies that alpha p plus beta q belongs to span of V1, V2, likewise till Vn. But that is exactly what we set out to check, right? That if p and q belong to the span of a certain set of vectors, then does alpha p and beta q, alpha p plus beta q, where alpha and beta are some arbitrary scalars, also belongs to the same set, same subset, that is the span of V1, V2, V3, so on till Vn. And the answer is a resounding yes, as we can see here, isn't it? Once we see that, we have actually proved it. Yeah. So it's very important to also be able to draw your conclusions on what we were trying to shoot for and what we managed to prove. So now you know that the proof is concluded. So when I say that I have just given you an outline of the sketch, basically I have given you all the working steps here. Only thing is that whatever I am saying in words now, you probably in a formal proof you have to write them down. Yeah, that's all that remains. So maybe after this you will just write this down formally, and therefore alpha p plus beta q belongs to the span, and hence this span that we set out to test for its applicability, for its credibility as a vector space, has indeed managed to pass the test, and therefore the span of a set of vectors is a vector space, and therefore it is also a subspace of the original vector space V, right. Okay. So, we have assured ourselves that this is it, but now the moment we come across this thing called a span, something else hits us immediately, and this term you might be familiar with from earlier on. What is that term? Well, that term is basically something called a linear combination. You see, excuse me, the way we have defined this, okay. So, given a collection of vectors, say v1, v2 dot 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 till vn, any vector v is equal to summation alpha I vi, I going from 1 through n, is a linear combination of the vectors v1, v2, so on and so forth till vn, right. So, now that you know that this is what the linear combination, the way it is defined, right. You have, of course, I am sure you have come across this description earlier. If you have done just course on simple matrix, matrix operations, maybe at your +2 level, high school, then you might have already come across this, I am sure. So, this term linear combination is something that is not very unfamiliar, I suppose, to most of you. So, in view of this linear combination, we can now, in words redefine what a span is. So, then it turns out that given a set of vectors, a span is a collection of all those vectors which can be written as a linear combination of the vectors in that given set. So, here is how it is. I give you a set of vectors, right, and you give me a collection of all possible vectors which can be written as a linear combinations of that given set of vectors, and this collection is indeed what the span of those given set of vectors is, right. So, in words that is what it is. So, that is why the moment you define a span, it is imperative that you also define what a linear combination is supposed to be. And it turns out that the moment you define what a linear combination is, the next important term that you will come across is again something I am sure you have heard of earlier, is so called linear independence. So, what is linear independence of a set of vectors? So, here is what it is. Suppose for a given set of vectors v1, v2 till vn, we have that c1 v1 plus c2 v2 plus dot 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 till cn vn is equal to 0 implies c1 is equal to c2 is equal to c3 is equal to so on and so forth till cn is equal to 0. Then we say that the set v1 v2 till vn is a linearly independent set. Okay, that is what linear independence is. So, let us sort of summarize this, whatever we have done so far. First we saw this, what a vector space is, then we saw what a subspace is, then we saw some example, like you take the vector space to be the set of all matrices, n by n matrices, and we saw that the set of symmetric matrices, real matrices, the set of symmetric real matrices forms a subspace thereof, right. Okay. Then we came to this more abstract example of a subspace, a span, right. So, we say that if you have any vector space defined, then you take a collection of vectors from that vector space and you define something called a span of those vectors, those set of vectors, yeah, and that also turns out to be a subspace. So, we defined what a span is, and we saw that indeed that span is also a subspace. The moment we defined the span, what immediately struck us was the way in which every member in that span is represented. It turns out that every member in that span is basically a linear combination of the set of vectors. So, that brought us to the definition of what is a linear combination. Having seen what a linear combination is, a very related notion then hits us straight in the face, which is that of linear independence, right. So, now we see that if a linear combination of a set of vectors, notice this very carefully now, because here before your screen you see the formal definition of a linearly independent set, but now I am sort of paraphrasing it into words in terms of the terms that we have just defined already, yeah, and listen to this carefully. So, what I am saying is, if you are given a set of vectors and if a linear combination of that set of vectors leads to the 0 vector, only if all the scalars in that linear combination happen to be 0, right, then you say that that set of vectors is linearly independent. So, again look at this, what is this on the left hand side here? What you have is a linear combination of the set of vectors, that is this set. On the right hand side you have 0. So, the only way the left hand side can equal the right hand side is when the scalars, each of them turn out to be 0, yeah. So, that is what linear independence of a set of vectors is. Not a very difficult notion, I am sure all of you have at some point in time or the other made use of this fact that a set of vectors is linearly independent and therefore we can carry out certain operations, so on and so forth, right. If you have dealt with matrices, you probably already figured out what I am talking about, but more on that probably later. For now we are going about it in a more formal approach. So, let us proceed along this path, right. So, the moment we have this idea of linear independence of a set that is linearly independent, next important notion would be that of basis. Okay. So, what is a basis, right, and again we would describe this basis in two different ways, one which is a formal description and the second description would be in words, trying to paraphrase the definition in terms of the terms or the definitions that we have already seen prior to this. Okay. So, that would be our approach towards a sort of a comprehensive understanding of this notion of basis. So, what is a basis? So, let us say, suppose we have a vector space V and a set B, of course that B is a subset that is contained in V, right, B, such that, so let me just for the sake of simplicity just B looks something like maybe V1, V2 likewise till Vn, I do not know. Okay, so this is just what it maybe looks like. So, this is just within parentheses, you do not need to read this. This is just something that I have just given you to get some idea about what this set called basis looks like. So, suppose we have a vector space V and a set B of vectors, set of vectors B, of course these vectors come from the original vector space V, such that any vector in V, yeah, can be written as, or rather let me say any vector V, any vector V in V belongs to the span of B. Further, suppose B is linearly independent, right, then B is said to be a basis for V. So, there are two things that a set within a vector space must satisfy in order for it to be a basis for that vector space. One, it must be a so called spanning set. In some texts you will also see the term called generating set, right. Secondly, it must also be a linearly independent set. Now remember, we have already defined these terms, and there is a reason why we are proceeding in this sequence, right. So, we know all the key terms that constitute the definition of a basis, we have already defined them. Yeah, you know what a vector space is, you know what a set is, of course, intuitively you understand. Then you know what the idea of a span is, you also know what the idea of linear independence is, and now based on all of these ideas that we have already introduced to you earlier, now we are defining this new idea called the basis. Okay? That is what a basis is. And as soon as you have defined a basis, the next most obvious definition that follows from this is that of dimension. So, what is the dimension? The cardinality of the basis for a vector space V is called the dimension of the vector space V. What is the cardinality? The cardinality of a set. Remember, what is the basis? Basis is a set. So, you have to distinguish between these objects. V is a vector space, B is not a vector space, B is a set. So, do not try to compare apples and oranges, okay. Yeah, there can be sets within a vector space which are subspaces, and there can be sets like the basis within a vector space which are not subspaces themselves, right. Yeah. So, be very sure to sort of carefully follow as to what ideas are being talked about, what sort of objects are we talking about, okay. Basis is a set, not a vector space, and therefore, it makes sense to talk about the cardinality of a basis, because it can have a finite cardinality. Cardinality means, so maybe for those of you who are unfamiliar with the idea of what is a cardinality, you can just think of it as the number of elements in a set. So, for example, if a set has 5 elements, its cardinality is 5. If a set has 5 million elements, its cardinality is 5 million. If a set has infinite number of elements like the set of real numbers, then its cardinality is just infinity, right. So, that is the notion. So, hand in hand with the idea of basis, you immediately get the idea of the dimension of a vector space, right. So, all of these ideas, you see, they are very much intertwined with each other. So, now I am going to make certain claims. If you are interested, again you can try proving them. So, think about it this way. Now, if I say, so these are the conventional definitions I have given you, by the way. Now, I am going to make some claims, and you just think about it for a while. Maybe I will just walk you through some of the ideas that constitute these so called proofs, but just think about it, and I am sure you will get there pretty soon by yourself, even without my assistance. So, what I am now saying is, for a set V1, V2 dot 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 Vn to be a basis for a vector space V, n must be the, listen to this very carefully. So, these are some of the claims I am making. N must be the what? N must be the smallest number such that span of V1, V2 dot 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 till Vn is equal to the vector space V itself. What am I saying here? So, this set of course belongs to the vector space V. Every member in this set belongs to the vector space V. Yeah. So, this is so far up until here it is a set, but the moment I call it a span, then it becomes a vector space. This is a subset, this is a subspace, remember that. I might be going a little fast with this because of course this is not linear algebra course, but please do make sure that you understand what objects are being spoken about here. So, we are saying that for a set each of whose elements come from the vector space V, right, to be a basis, yeah, we must have that n. What is the n? The n is basically the dimension, no? So, n must be the smallest number such that this is a spanning set. So, in other words, alternately I can say, hang on, so in other words I can say that the basis is the minimal spanning set for a vector space. What do I mean by minimal? Minimal in terms of the cardinality or the number of elements in it. Notice very carefully what happens. If the number n, the number of elements in this set is not really as small as it can be, right. So, that means it contains some superfluous vectors in this set which need not have been present in this vector space in this set after all, right. So, that means we could have spanned this vector space using a smaller number of vectors. Yeah. So, that means the next conclusion to draw is that we have more than we need. So, we could have eliminated some of them. What does that mean? That means that some of those elements which are additional. So, maybe let us say we could have actually spanned this entire vector space V using a smaller number, say n bar of vectors, right. So, the additional n minus n bar elements, these are superfluous, these are redundant, and we could represent any one of these elements using the remaining n bar elements only. What does that mean? That means that this set is not going to be linearly independent, because some of the vectors in that set can be represented as a linear combination of the other vectors. What happens when that is the case? Suppose you have Vn is equal to summation any number, let us say beta I Vi, I going from 1 through n minus 1. That can be alternately written as, just summation beta I Vi is equal to 0, where beta n is just minus 1. But then, that means that, well, so if any element in a set can be represented as a linear combination of the other fellows in that same set, right, then what we can definitely say is that the set is linearly dependent, because it violates the tenet. Look, for linear independence I required each of the betas to be 0 here, but I already know that this last element is not 0, and neither are some elements potentially here, right. So, therefore, that set is not going to be linearly independent, but for it to be a basis we need the set to be linearly independent, as we have said here. So, these are like alternate ways of defining this. So, either you say that a basis is a set which is linearly independent and is a spanning set, or you say that a basis is a minimal spanning set. One follows from the other. If you are just interested in defining a basis from the spanning aspect of it, you just say it is a minimal spanning set. That automatically implies that it will be spanning as well as linearly independent. Or you say it is linearly independent and it is spanning, and it will automatically imply that it is a minimal spanning set. What about the linear independence aspect? Well, from there we say that the basis is a maximally linearly independent set. Okay, what do I mean by maximal? Again, maximal refers to the number of elements in that set, Okay, so when I say maximally linearly independent set, what do I mean? It means it contains just enough number of vectors for it to be linearly independent. That means, suppose given that set of basis vectors, that n elements that I have given you there, if you picked out just any other arbitrary vector from that entire vector space and appended it to this set so that the set contained more than n elements, there is no way that this set could have been linearly independent anymore. Okay? So, a basis can be defined in either of these ways. It is a linearly independent spanning set, that is one definition. An equivalent definition is it is a minimal spanning set, and just as well you could have also defined it as a maximal linearly independent set, right. So, how does it follow from the original definition? Just let us try to build that connection here. The basis is a maximally linearly independent set. This, as I said, also means that the basis is both linearly independent and spanning. So, of course, if it is maximally linearly independent, then it is obviously linearly independent. But how is it also going to span, right? Because now it means that, well, if it is maximally spanning linearly independent, then you take any other vector and append it to this set, and that vector can be written as a linear combination of the other fellows, which means that that vector belongs to the span of this set. So, even when you call it maximally linearly independent, you are automatically saying that is not just is it linearly independent, but it is also a spanning set. So, all these three definitions of the basis are one and the same, they are equivalent. Okay? If you want a more formal treatment of this, again I urge you to write this down in a more formal fashion, but of course, as I said, the purpose of this course is not really to get there with linear algebra per se. So, we will only just touch upon these topics in the way that I am doing now, and I hope that you can draw the connections between these concepts and these ideas, right. So, now having seen all of this basic ideas about a vector space and the notion of what its basis is, what its dimension is, what the span of a bunch of vectors in a vector space is like, yeah. The next idea we shall introduce is one of coordinates. Now, if some of you have come across this term called vector space, the most common vector space that you have probably seen are n tuples of numbers, Rn or maybe Cn. So, those numbers could be real numbers or complex numbers, right. So, those are just written stacked up in a form of n tuples, right, and you immediately relate them in case of Rn to the Euclidean space. Yeah, each of those entries in the n tuples is basically a coordinate, all right. Now, the point is that we find this a very convenient way to represent a particular vector, right. So much so that this representation itself in the Euclidean space is a vector, right. So, you have the 3-dimensional coordinate system here, and you have this point, let us say 1, 1, 1, and we say that this 1, 1, 1, this is basically a vector in R3. But it turns out that even if the vector space that you are dealing with is not necessarily the Euclidean space, you can equivalently represent it in terms of coordinates just like you represent vectors in the Euclidean space. How so? Quite simply, it is this basis that allows us to do this. Okay? So, how do you do that? So, suppose a vector V in the vector space V can be represented in terms of a basis B is equal to V1, V2 dot 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 till Vn, such that V is equal to alpha 1 V1 plus alpha 2 V2 plus dot 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 plus alpha n Vn, then we say that a coordinate representation of V in terms of the, and here is a new thing that I am going to introduce now, in terms of the ordered basis. So far I have just been talking about basis, now I am just introducing this notion of ordered basis. So look, when you just give a set, Yeah, I give you a set of numbers, let's say 1, 2, 3, and if you don't put any order on the numbers, so then you say that, well, I have written the set as 1, 2, 3, and you write the same set as 2, 3, 1, and somebody else writes the set as 1, 3, 2, yeah, all sorts of permutations. So these do not matter, these are still the same set after all, right. But now when you introduce this idea of ordered basis or an ordered set, then the order does matter. So when I am writing this B in this way, that V1, V2, V3 dot 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 till Vn in this order, and I am specifying the order for you, then it's like cast in stone. You cannot play around with it, you cannot permute these elements in the basis set, all right. So that's why we say it's an ordered basis, a basis with a order that has been defined, yeah, that is an ordered basis. Okay. So then we say that a coordinate representation of V in terms of the ordered basis B given by V within the box bracket V is written as VB is equal to alpha 1, alpha 2, and what does this remind us of? This is something that now belongs to, well, Fn, in our case maybe Rn or Cn, right. So you see, irrespective of what the actual vector space looks like, in other words, what every member or element in that actual vector space looks like, we can always represent it as an element in the Euclidean space. Of course, again, subject to the fact that your scalar is a real number in this case. How so? Through a basis. You know that the representation of a vector in terms of this basis, how it is, and once you have defined the order of the basis, you cannot just switch alpha 1 and alpha 2. So then, you know, the first entry of this element here is just going to be alpha 1, because you fixed it up through this ordering. That is why this ordering is important. Something that is implicit here, and I have not really highlighted too much, but again I urge you to check. Okay, I'll just talk you through how to prove it. I'll not have time to discuss all of these proofs in writing, but something that is inherent in this is representation of a vector in terms of a given basis is unique. Okay, that is what makes this mapping or this coordinate assignment possible, because if this were not unique, then you take a vector and a particular choice of basis and you get a certain point in the coordinate space, in the Euclidean space, and I might have chosen that same vector and that same basis, and I might have got some other point in the coordinate frame in the Euclidean space. That's not very helpful now, is it? Right? So of course implicit in all of this is the fact that this representation is unique. Why should it be unique? So just as an exercise, you try this out. Let V be represented as alpha 1 V1 plus alpha 2 V2 plus dot 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 till alpha n Vn. Suppose there is another alternate representation, say alpha 1 bar V1 plus alpha 2 bar V2 plus dot 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 till alpha n bar Vn. Yeah. Then what would be the case? You can equate them. So on one side you have alpha 1 V1 plus alpha 2 V2 plus dot 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 till alpha n Vn. On the other side of the equality you have alpha 1 bar V1, alpha 2 bar V2, alpha 3 bar V3, so on till alpha n bar Vn, right. Now you bring everything on one side. So what is the coefficient of V1? Alpha 1 minus alpha 1 bar. Coefficient of V2, the scalar multiplied with V2, alpha 2 minus alpha 2 bar. Scalar multiplied with Vn, alpha n minus alpha n bar. And on the right hand side you have 0. So you have a linear combination of the set of vectors V1, V2 dot 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 till Vn equaling 0. What do we know about the set of vectors V1 through Vn? They are linearly independent. Now if a set of linearly independent vectors has a linear combination which equals 0, when is that possible according to our definition? It is only possible if each of the coefficients is in turn equal to 0. But what are the coefficients? The coefficients are alpha 1 minus alpha 1 bar, alpha 2 minus alpha 2 bar, dot 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 till alpha n minus alpha n bar, which means that each of them must vanish, which means that alpha 1 is equal to alpha 1 bar, alpha 2 is equal to alpha 2 bar, which then in turn means that the representation is unique, right. So you have to read between the lines sometimes. Not everything will be really proven to the point like as would be done in a typical linear algebra course, right? But I urge you to practice this because only then you will get a deeper insight into what's being done here, right? So we have seen what? We have seen the idea of a vector space, we have seen the idea of a subspace, we have seen the example of a typical example of a subspace being the span. We have seen in view of the definition of a span what linear combinations are. We have seen in view of linear combination what linear independence is. We have seen based on the ideas of linear independence and linear combinations and so on and so forth what a basis is, right? Based on the idea of a basis that we developed, we have seen what the dimension of a vector space is, right? And we have seen that based on this dimension we can now also map any vector in any arbitrary vector space, of course of a finite dimension, to some point in a suitable Euclidean space of the exact same dimension. So if you have an n dimensional vector space V, you can always map every vector in that vector space V to a point in Fn, in our case it will be Rn or Cn as the case may be, right. So we have seen all of this. In the next lecture we shall start with what is the idea of a linear map, right, and we will see that because of this idea of this coordinate, it leads us to this beautiful conclusion that any linear map between any two arbitrary vector spaces, those vector spaces could be abstract vector spaces, not necessarily Euclidean spaces, right, they have a corresponding representation in terms of a matrix. What is a matrix after all? A matrix is a linear map between two Euclidean spaces of potentially different dimension, different sizes, right. So every linear map between two vector spaces can be related to a matrix between two Euclidean spaces which transforms a vector in one Euclidean space to a vector in another Euclidean space, and subsequently we will introduce the ideas of the rank of a matrix, and we will see that this rank of a matrix also relates to the size of the so called image space of the linear map that we have defined in the abstract vector space, okay. So more of those concepts to be built on later, but be assured that the ideas we have developed in today's lecture will be harnessed to great benefit in what is to follow subsequently. So till then, take care, thank you.